Hello. In this video on understanding physics and mathematics, we're going to continue on talking about computational physics. In particular, we're going to talk about time evolution. This continues from the last video because, as you remember in the last video, we were using Excel to basically look at the trajectories of projectiles given one dimension, two dimension, three-dimensional model, wind resistance, and the like. We were using Excel in that example and Euler's method. Today we're going to use a little bit more elegant software package and a little bit more powerful software package to try to build on our knowledge and try to approach a little bit more complicated systems. All right, to do that, I encourage you to go back to the previous video if you don't understand Euler's method and the idea of time evolution. But we're going to move forward here and use something a little bit better than Euler's method, or an extension of Euler's method. In particular, we're going to use what's known as the Runge-Kutta method. The Runge-Kutta method, and sometimes this is called the fourth order ordinary differential equation method, or RK4, as I'm highlighting here. And this is just a Wikipedia page if you're interested in the details. But basically, the Euler's method basically starts at t0 and uses the information at t0 to get information at t plus delta t. The fourth order Runge-Kutta does something even more clever than that. It actually uses information halfway along the step. So it uses information at t equals 0, t equals delta t over 2, and t equals t plus delta t. So it's going to use all those informations and kind of average this out. This is what you see here. It's going to use information at the beginning of the time step, the middle of the time step, and the end of the time step. Again, if you go into a computational methods class, you might learn more about this in detail. In our case, we're just going to basically use this method inside the software. The software package I'm going to use to go beyond Excel, and if you remember, this is our Excel spreadsheet we made last time where we had time, position, velocity, and acceleration. And the new time is just the old time plus delta t. The new position is just the old position plus v delta t, and so on and so forth. And then we just copied this down. All right. We're going to do the same thing now, but we're going to use a program, a software package called Octave. This software package is very similar to Matlab. Octave is a free and open source version, but it basically runs on the same commands. Notice that you could use Java or Python or any number of libraries, and that's perfectly fine. And they work in much the same way. So let's go ahead and get started looking at some details, and we'll start out with some details of how Octave works. All right, so Octave is a language you can type things like a equals 1, right? And it will run, it will store a equals 1, right? Let's start out by doing a clear all. That just gets rid of all the information that I had stored. So a equals 1, I can say b equals 2, I can say c equals a plus b, right? So it can do all the standard kinds of mathematics, and it will output those numbers down here. But it's also nice because it can do plotting like we see on the right-hand side, and we'll get to that plotting very quickly, right? So in many situations, it's much nicer than something like C or Fortran or a more a lower level language, because it's very easy to take your results and plot them immediately. All right, so a few things we need to know about Octave. To start, one, we can also define functions. All right, so to define a function, you just say function, and the function is going to have a few parts. So we'll call this function test function, and we'll say, let's say x in and x out. All right, and then we'll want to end the function. All right, in this definition, we're defining a function. The function name is whatever I write here. In this case, the function name is test function. Anything on the right-hand side in these parentheses is going to be the input parameters. Anything on square brackets on the left-hand side is output. So I can say x out equals, well, x in plus 2. And if I do that, whoops, plus 2, hopefully you can see how you should be able to see that. And if we do that, we can just call this function test function. And if we put in a variable like 4, right, and I run this code, I see that the answer is 6, right? It's just 4 plus 2. But I can also do things like, square it, right? And now if I run it, it's going to be 16. And hopefully that's large enough for you to see there in the corner, okay? Actually, let's scoot this over just a little bit so it's easier for you to see. There we go. That's a little better, right? So the answer is 16. So you can have anything in here, and you can also have A, B, C. You can have any number of input parameters you want and any number of output parameters you want. I will caution you that Octave and Matlab are slightly different. Octave wants you to define the functions at the top and then use the functions in the body. Matlab wants you to use the functions and then define the function at the end. All right? So just be aware of that slight difference between the two. All right. So another nice thing is percent signs leave comments. So this is just our test function. And I've done this function. Now let's also look at, let's move this over. Let's look at something like our simple, let's try to do something like our simple time evolution that we did before in Excel, but now let's do it here in Octave. All right. And we're trying to get something like we have here on the right. So let me just do that. So let me just clear this thing we have on the right. We'll discuss this here in a moment. Okay, that was just to get rid of it. So if I want to do that, then I need a starting time. Let's call that T0. And let's start at 0. Let's say T final equals 10. And let's say dt equals 0.1. Okay, so that defines my starting time, my interval, and my finishing time. To do a for loop in Octave, we just say for. This is like copying down the lines in Excel. And we say t equals t0 colon dt colon tf. And then we do it again. So what does this mean? This means I'm going to loop over the variable t. I'm going to start at the value t0. Each loop, I'm going to add dt to this value until I get to this variable. All right. So let's go ahead and just output t here to see what this looks like. If I do that and I run the code, you can see down here at the bottom, hopefully, that I get, and let's just make it go to 1 so we can see it a little better. You can see I get 0.1, 0.2, 0.3, 0.4, keep on going here in the times, right? So it's just looping over the times. So let's see what we have. Let's say our velocity, let's say equals 10 meters a second, all right? In this case, what's our position? Well, let's say our starting position is 0. So what's our new position x? Our new position x just equals the old position x. And this is something you'll have to get used to in programming language. You're overriding the variable with itself. And so x equals x, so this was the old x, plus v times dt. All right? So the new position x equals the old position x plus velocity times time. And this will go ahead and calculate the velocity. But you can see this is not very great. It did it, but it didn't show me anything. It didn't tell me the number. So what I'd like to do is make sure that this is working. Let's actually plot this. And so I can plot things by just saying plot. And I'll plot t versus x. And this will be one of the first tricks we learn. If I want to see this in real time, right, plotting always overwrites the last plot. So this would just show, if I do this, on this graph on the right-hand side, and let's make them circles. On the graph on the right-hand side, there's just one circle because it just wrote the last thing. If I don't want it to overwrite, I use the command hold on. Hold on means don't erase the plot, just add new things to the plot. And I'll do hold off to turn that feature off. All right. Now if I do it, you can see what happens. So our velocity, so the bottom axis is time, and the vertical axis is position. And it's always good. Let's go ahead and get started by making this graph look nicer. So we can do an X label, and that X label is time. And we can do the Y label. In this case, the Y label is position X. And if we want to make it a little bit easier to read, we can do this command. GCA, so set is just set, and then GCA, this just means the current graphical thing that's up. And you just do font size. And let's make this really big for the video, 30. Now if I run this, now hopefully you can see we have X on the vertical axis, we have time on the horizontal axis, and we have these points as we're stepping along, right? So this just says our position increases linearly as we're going. And of course, I could change any of these parameters, so I could change dt equals 0.01, and this just means I get more points along this line, right, in this thing. That's fine, but that might not be the most interesting thing to look at. Let's instead make the acceleration equal to 10 and the initial velocity equal to 0. This would be like dropping a ball. So we still have the acceleration, and remember, using Euler's method, that the velocity is a lot like the acceleration. So the velocity equals the old velocity times the acceleration dt. Okay, so we're looping over the time again. Yeah, and to clear the plot, sometimes it doesn't want to clear the plot, so let's just do plot 1, 1. So that was just there to clear the plot. And now let's run this again. And in this case, I have a constant acceleration. I'm letting the velocity using Euler's method, right? By definition, the acceleration is the derivative of the velocity. So the fundamental theorem of calculus says the new velocity is just the old velocity times the slope in the velocity, which is acceleration, times the change in time. And the same thing for x, only depending on t. And now if we plot it, as one would expect, we get the 1/2 at squared. All right, so it's just that easy. Now, basically, we've already caught up to everything that we've done in the Excel videos. Okay, so what we'll do next is we'll expand this a little bit and actually use some of the built-in functionality. Okay, so to do that, we'll use a different equation, a different function, right? And almost all of these software packages, Matlab, Octave, Java, Python, etc., are going to have something that looks like this function. All right. And again, just Google ODE45 or fourth order Runge-Kutta and the programming language you're working in, and you'll be able to find this. All right. So this ODE45 means the fourth order ordinary. So ODE, ordinary differential equation, fourth order. All right. What we did here was the 0th order, or the first order solution. This is the fourth order using that Runge-Kutta we looked at on the website before, right? And let's look at what this needs to work. So for this to work, it needs several things. It needs x0. x0 is just the initial conditions. So let's say x0 equals 0, right? So these are just if I can spell, conditions. So these are just the initial conditions. We need something else. We need the time span. The time span, we can, later on, probably not in this video, but in a later video, we'll see that we can actually let it determine its own time span. But in this case, let's just keep it simple and say, let's go from t0 dt, t0 dt tf. Just like we did right here, right? So we're going to copy this down to our new section. And why don't I just comment this out at this point so we know that we're not actually running this code anymore, right? So Control R is a shortcut key for commenting it out. So we have the time span now. So this is the time span of my calculation. This is the initial conditions of my calculation. And now I have to deal with this funky looking thing. Well, ODE 45, what it wants is a function that returns the derivative, right? So it will do the rest, but what you need to do is give it a function, and in this case, I'll call this function A. So we need a function, and that function, in this case, we just call it A, that's fine. And remember, the form of a function is the outputs equals the name of the function type, and then inputs. So we're going to input, in this case, x in, all right, and the time, all right, and let's just call it x, all right. So the input function needs to take, and exactly in this order for this ODE 45 to work, it needs to have a function that takes in the time and then the position. And what that function needs to output is the derivative. So dx dt is what it needs to output. All right? So if we go back to our first situation with a constant velocity, that means velocity, let's just say velocity equals 10. All right? So what's dx dt? Well, dx dt just equals the velocity. All right? So notice that I am just outputting the slope of the inputs. So whatever I input, in this case x, I want to output the time-dependent derivative of that function. All right? So notice that I'm not even using these two. Later on we'll actually use those two. But if I do this, then basically I have everything I need to do the ODE 45. That is, I have a function of t and x, I have a time span, I have the initial conditions, and we'll get, and this is just, this is just to make sure the computer knows what I'm doing. This is the @ sign just means it's a function of these two variables. So later on we might have more variables there, right? So this will become obvious later on why I want this to be here. But right now it doesn't make much sense because I'm saying I have a function of the variables t and x, and it's a function of the variables t and x. So it's kind of repeating itself, but later on it'll become apparent why I want that there in the general form. So when I do this, and now this should run, hopefully, let's check, good, it runs. And what this outputs then is plot t and x. And let's go ahead and, let's go ahead and copy our things here so we can make sure that these look nice. So we're going to plot t and x. Let's go ahead and run that. And there we go. So hopefully, let me just check that you can see this. Good. So on the bottom is the time, right? The horizontal axis, you can barely not see the time. If I move over, you could see the t right there peeking out behind me. So you have the time, and on the vertical axis you have the position, and this is exactly the same graph we had before. And if we want to look at it as each individual part of the plot, we could just put that. That just means plotted as circles. So this is the solution. All right. Again, just to make it clear, what am I doing? What is this doing? I have a function of the time and the position, and what it outputs is the derivative of the position. In this case, it's just constant velocity, so it outputs the velocity, and what comes out of this ODE 45 is the solution for the time and the position. All right? I think it's helpful to think of this something like you're driving in a car, and every second you read out, you're on the phone with me, let's say, and you're in a car driving, and every second you read out the velocity of the car, okay? If I wrote down those numbers and the times you told me those numbers, I could tell you what your position was, right? Because you tell me your velocity, and that's how fast you're changing your position, so I could map it out. And that's what this, basically this, the function and the ODE 45 is doing. I'm telling you the slope of the line at each point in time, and then this function is telling me the position as a function of time. All right? So that's interesting, but this is, of course, constant velocity. What we're typically more interested in is constant acceleration. All right? So how are we going to deal with constant acceleration? Well, if we have constant acceleration, now we're going to have multiple initial conditions. All right? So let's say x0 equals 0 and v0 equals 0. All right. But I have to conform to the way the computer wants to get this information. And the computer wants to get this information inside this variable. So I'm just going to call this initial conditions. And initial conditions is going to be all the initial conditions. So it's just going to be x0, comma, v0. All right. And later on, we'll see we can have even more initial conditions. But in this case, the initial conditions are just the initial velocity and the initial position. All right. So those always have to go at this point in time. All right. And I'm going to actually, I'm going to copy this down here just so we always have this this original kind of form so we know what's going on. All right. Time span is still the time span. The function is still the function. I'm going to rename the function. Let's call the function b instead of a. All right. So let's call this one. This one was a, but we need to make a new function. We'll call that function b. So in that case, now the things I need inside that are going to come in are the position and the velocity, not just the position. Okay? But again, I have to conform to what the computer wants, and the computer wants all the variables inside x, inside this thing that's called x. So the x input is actually equal to x1. x1 is just the first value that's inside x. Okay? And then v input is just x2. All right? That's just how I'm passing the information to the computer. The first number is x1, the second number is x2. Okay. Now the acceleration is going to be 10. I'm going to make that acceleration a constant. That's fine. But now if I have two inputs, I have to have two outputs. So I'm going to have dx dt1, and I'm going to have dx dt2. All right. What does this mean? Well, dx dt1 is just the derivative of whatever this input was. What's the derivative of the position? Well, the velocity. So this one is really easy. We're just saying the input velocity is the output velocity, right? This is the derivative at that point in time. All right. What's dx dt2? Remember, x2 is actually the velocity. All right. So what's the derivative of the velocity? The acceleration. Okay. So let's go ahead and see if this works. Yeah. And there we go. It's really that simple. But why did I get two pieces of information? If you look on this graph, you see I have a straight line that's red and a curved line that's blue. Well, that's because I asked it for two pieces of information. So I gave it position and velocity, and so it's going to output position and velocity to me. All right. So we also need a little bit of housekeeping here. So x out, in this case, it stores it inside the x and inside position. Okay. What the heck does this mean? All right. So it's going to output the time. The time is just a time. That's easy. But inside this x, right? Again, the computer insists on this form. So inside the x, it's going to store all the variables. Okay. And this in Matlab is just saying, give me the first, this one means the first part, and this means everything. So give me all the x values, and I'm going to store that as x out. And the second one is the second derivative, and that's v out. And now we can plot both of these, x out, t v out, and we can even be fancy here and ask what the legend is, and the legend is going to be x, comma, v. Let's go ahead and run that. Oh, it helps if I write the right numbers. And there we go. So you see the legend here, right? V is the circles, and V just increases linearly in time. And let's make these circles as well. And the position just goes like 1/2 AT squared. If we want to, we can look at what the analytical solution to this is. Remember, this is just t and 0.5, 1/2 times 10 times time squared. Oh, time. So this is just 1/2 AT squared, right? This is just a solution because I gave it constant acceleration up here. All right. So let's see how good our numerical simulation worked. It works so well you can barely see the line inside the circle, right? So I can play another trick to show this a little bit. So let's make the line width larger. All right, yeah. Just so you can see it. So I'm plotting the X out, the T out, and then I'm plotting the analytical part, and I'm making it bold. And let's call this theory. And let's plot that again. And you can see how incredibly well that matches, right? Even if we make our time steps, so let's make our time step 0.1. Even if we make our time step 0.1, it still matches very, very well, all right? This is starting to show the power of this fourth order Runge-Kutta. If you were just to do this in Excel, or we were just to do this up here with our for loop, we'd need very fine time steps for it to match the analytical solution. But the fourth order Runge-Kutta is a much better approximation, and so we need much fewer time steps for it to match. All right? So again, a quick second here of review. What we're using is ODE45. This is a built-in function in Matlab or Octave, and it's a built-in function in many different programming languages. ODE45 needs the initial conditions. That's where you're starting, because remember, ODE45 is basically doing something very much like this time evolution, right? So you need the initial conditions. You also need the time span over which you're doing the calculation. Again, this is like this for loop. You need to define the time span. And then the final thing it needs here is a function that returns the time derivative of all the variables you input. All right? So in this case, we input position and velocity. Namely, we input xn and vn. And what does it output? It outputs the derivative of position and velocity. The derivative of position is velocity. The derivative of velocity is acceleration. Okay? So that's just how simple these kinds of things can be. All right, let's go ahead and do something. We talked about wind resistance or drag. Let's see how easy it is to do that. So let's do this again. We can basically, what's an easy way? Let's copy this. Let's copy this. Yeah, and we can get rid of, we can basically comment all this out. Okay, so let's go ahead and do this. We'll get rid of this. So we're going to do our same T0, TF, dt. Initial conditions, time spent. Great. But let's do this one with drag. All right. So I can call the function anything I want. I'm going to call the function drag. All right. So what is the drag in this case? So let's say it's one-dimensional motion. All right. So let's say I'm dropping a ball out of an airplane. If I drop a ball out of an airplane, then this is minus 9.8. This is gravity. But I also have wind resistance pushing back. And this wind resistance, let's make it 0.01. This would be the coefficient of friction, right? Times, and let's make it linear. So let's just say times linear velocity. All right. I need a few things, more things in here, like the mass and to deal with some things there, but let's just go ahead and roughly make it work to make sure it's working first. All right. So now we start to see the power. This acceleration doesn't just have to be a number. It can be a function of velocity. It can also be a function of position. It can also be a function of time. All right. So we have minus 9.8 minus a drag coefficient times this guy. And basically everything here can be exactly the same. And let's see, okay. Now let's try to run this. Hopefully we don't have errors. Something interesting happened. It of course doesn't help when you call the wrong function. So I called the old function b. It's probably a good idea to make this the new function drag. Let's try that again. Good. So I drop it, and well, let's just make this 0 to start with. So if I drop this, you can see the theory and the calculation go together, and this is the velocity. But if I start to add drag to this guy, and let's extend the time frame to around 10, and there we go. Now we have the theory, and let's increase the drag a little bit more. And now we see we have something. Let me make sure you can see what I'm doing here. Yeah. So what do we see here? Well, the velocity and the position are here. So the line is the theoretical, but the line is the theoretical without drag. All right. In this case, the blue dots are not going to accelerate more because you're going to reach terminal velocity. Let's go even a little bit further out in time. There we go. And if we go far enough out in time, that was maybe a little bit excessive. So if we go further out in time, you can see near 0 here, hopefully you can see my mouse, it's going to follow this theoretical curve for dropping in a vacuum, but then the velocity is going to be equal to a constant, and that constant is the terminal velocity, and the position is just going to change linearly, right? So it was really just that easy to add in a coefficient of linear drag, all right? And now you're starting, hopefully, to see the power in this method. It seemed complicated before, but realize all this stuff where you're defining what the computer likes and that it has to be in this form, that is just kind of boilerplate. Once you do that, you don't really have to do that again. And all I am changing is basically this one line that describes the physics. All right. And you also see how quickly it's doing this computation. All right. So let's go ahead and make this a little bit more correct. Right, this is a force. So of course the acceleration is the force divided by the mass. All right, and this is the coefficient of linear friction. So let's call that B. Maybe it's not good to call it B. I'm going to call it CL for coefficient of linear friction. So that means I have the coefficient of linear friction and the mass need to also come in this equation. How can I do that? Well, obviously I can put them here. CL and M, that's fine. But again, my ODE 45 doesn't want to deal with that. And this is why I did this in this particular way, is because now I can do CL equals 0.1 and mass equals 1. Mass equals 1 here. So the nice thing about this is this says that the only variables are going to be t and x. Everything else, plug in what I already told you. So it says that plug in this c and this m get passed into the function, but ODE 45 doesn't care about them. It treats them as if this value of 0.1 was stuck in there and this value of m was stuck in there. Okay? So now it should run exactly how it ran before, right? But I can change things like the mass. If I change the mass, of course, right now the force of gravity is very much stronger, and so it's going to have a larger terminal velocity, and so it's going to match closer to the line. If I make the mass small and do the same thing, you can see it reaches terminal velocity much earlier, and I can also change the coefficient of linear friction. Okay? So it's just that easy. I can also make this minus quadratic. So coefficient of quadratic friction times, in this case, Vn times the absolute value of Vn And I'm playing this trick of taking Vn times the absolute value of Vn because I want the direction, right? So this is going to give me the direction, whereas if I just had Vn squared, it would lose the direction. So I have Vn times the absolute value of Vn divided by m. And let's do this CQ. And coefficient of, let's make sure we do, whoops. And CQ, the coefficient, and M, and now let's see if we have any errors. So that runs just as well, right? And so now we can compare things as if we want to look at linear friction or quadratic, right? So we have quadratic wind resistance. In that case, we have linear wind resistance in this case, and we have both in this case, all right? So I'm just defining what my acceleration is, right? Notice I could pass other things in here as well. I could also, maybe it's good to pass G in, so I could do the acceleration of gravity. So G equals minus 9.8. And so this is just G, right? And actually, well, it's G times M divided by M, so it's just G. Okay, and you can see this is nice because now all I need to change is these coefficients to see how things change with changes in the drag. If I want a different condition, I could also do things like, well, instead of just dropping out of a plane, let's say I throw it upwards from the plane. So I'm going to throw it upwards from, let's say, the top of a building, right? I'm going to throw it upwards at a high speed, and then it's going to fall. Well, what's going to happen? Well, it goes upwards first, and we can make it go very much upwards. We don't need nearly as much time here. Let's see what's happening here. V0 equals 10. Yes, so you can see, right, this blue line starts to go upwards. It's hard to see. If you want to, you can also change the limits on your plot. So let's go minus 10 to 10. So you can see now I throw it upwards, right, and it's going up and then coming down, all right? So I can also change the initial conditions, all right? So I could loop through initial conditions, I could loop through any of these parameters in a programming language, and it's going to do it for me. All right, let's get a little bit more complicated, now a little bit more interesting. We notice that this drag is just in one dimension, all right? What if I wanted to do something in more than one dimension? Let's say I want to do it in 2 dimensions or 3 dimensions. Let's go ahead and just jump to 3 dimensions. Again, I'm going to copy this so we can start over. All right, so in 3 dimensions, I'm now going to have multiple things. So I'm going to have x0, vx0, and if I'm working in 3 dimensions, I also need y0, vy0, z0, vz0, all right? And my initial conditions are going to be all of these. Again, I have to store all these in the way the computer wants me to store them, which is all an array. So my initial conditions, and again, I can change these if I want, but these are my initial conditions. My time span, again, this defines my time span. And now let's do, this is drag in 3D. So we'll have drag in 3D. Well, how am I going to deal with this drag in 3D? I just add more input parameters. So in this case, this is going to be x in, vx in, y in, vy in, z in, vz in, and these are all stored in my array. All right, so again, this part is just kind of housekeeping, and you get used to this as just being a way that the computer wants to store it. It wants to store every variable inside this x that's going to be changing. So we just store it in there and then pull it out so that we can use it and give it a name that we can deal with. All right. So let's say AX, let's start easy and say AX equals 0, AY equals 0, AZ equals G. All right, so now I'm just going to throw a ball and the gravity is going down in Z. Okay, easy enough. I don't need this right now, so I'm going to take this, I'm going to comment this out. All right, and so now we need the output. So the derivative of xn is vxn, and the acceleration, this is vy, this is ay, and this is vz and az. 2, 3, 4, 5, 6. All right. So again, all the physics is here, right? This is just housekeeping that the computer wants to be able to store these kinds of things. So we have vn, vxn, y, vyn, z, and so on and so forth. And in this case, we're just going to have it move in time. All right, let's go ahead and use these same parameters we used before. This will be fine. And let's do this. But again, a little bit of housekeeping. So it's going to be x out, y out, vy out, z out, vz out, right? Again, it wants to store everything in this form. And once you get used to it, it's not bad. You just have, it's always going to look something like this, and you're just going to add more variables in this row, right? You notice it just goes 1, 2, 3, 4, 5, 6, right? If you have more things, you'll add 7, 8, 9, and just keep going, and you'll call them in this way. All right, so let's go ahead and look, and in this case, it's three-dimensional, so we're going to plot in 3D, and we're going to plot x out versus y out versus z. Actually, let's plot x out versus y out. Let's start there. All right. Yeah. So let's go ahead and start there just by plotting that. And well, let's actually do z out. All right. So this is x and z. Okay, non-conformal. Da 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 da. Let's see. One, two, three. Drag. Of course, made the same error. I made a new function. I better use that new function and not the old function. Drag 3D. Yeah. And it gave me an error, but that's just because I gave it a legend with too many things inside of it. That's fine. But let's get rid of that. So you see there's no errors down here. Okay. So that looks pretty darn good. I throw the ball with an initial velocity in x and initial velocity in z, and it goes up and comes down just like we'd expect it to go up and come down, right? And I can even make the initial conditions this 0, right? So I'm basically throwing this at 45 degrees, and let's make this 5 just for convenience, right? And so you can see it goes up and comes back down. All right, we can make it more or less points, but it doesn't really change, right? It's doing just fine with the resolution we have. So that's maybe not, that's maybe not that impressive. In this case, I'm not sure why it's plotting. Oh, did I set the limits? Yeah. So let's take that away as 2. Yeah. So here's a trajectory in time and position. But let's actually look at it in 3 dimensions. In 3 dimensions, it's x, y, and z. And the label is going to be x, y, and z. Let's go ahead and do that. And let's also put the grid on. Good. And so now you can see that it's actually throwing it in 3 dimensions. So I started at 0, 0, 0. Those are my initial positions in 3-dimensional space. I throw it with a velocity of whatever I said here, a velocity of 10 in the x and a velocity of 10 in the z. So it makes this nice trajectory and just follows the line. Well, does it work if I change and add a velocity in the y? Of course. Now I'm throwing it at a diagonal, and it went ahead and traced this trajectory out. All right, let's go ahead and see if we can add the more complex situation where we have drag. So what's the acceleration in x? The acceleration as x is the coefficient of linear friction times this guy times Vxn, right? And the same thing for Vyn, and the same thing for Vzn. So if we have drag in this case, and we throw the ball, you can see it changed the trajectory that it's on. All right, so let's move it along. Let's keep it on the axis so it's a little bit easier to see. So initial conditions 0, 0, 0, v equals 10. Oh, it's playing a little bit with the limits, so let's change that so it looks correct. So let's do y equals minus 3, let's say, to 3, x equals 0 to 20. And let's do z equals also 0 to 5. There we go. So the plotting sometimes makes it appear a little bit strange. All right, so this is with linear drag, and of course I can increase this coefficient. Let's say it's 1, and you can see it reduces the distance the ball is thrown and changes the trajectory, right? And now it's in 3 dimensions, 0.1. This becomes more interesting perhaps when we add quadratic drag. So quadratic drag will need a few other things. For example, quadratic drag, we need the speed. I'll just call it s. And the speed is the square root of Vxn squared, Vxn squared, plus Vyn plus Vzn. All right. So this is, I forgot what I called this, coefficient quadratic times the speed times Vxn. All right, you notice that the quadratic drag depends on all 3 components, right? This is very difficult to solve in an analytical function because you're going to have coupled differential equations, right? But analytically, this is not difficult at all. We can just do this right here. Vxn, Vy, and Vzn. And this, I believe, should work. Yep. And so now we could turn off the coefficient of linear drag and turn on the coefficient of quadratic drag. And we can see how these things affect the trajectories differently. And we can also have both if we want to, right? We can change the mass, we can change the gravity, we can change the direction we throw it. All of these things are possible. Let's see, this video is getting a little bit long, but I want to show you one other example before we go. And notice I could do things like I could also add in, for example, wind here, right? And I could change the velocities and the wind resistance, right? So then I'd have, let's say, Vx prime, which would take into account the wind velocity as well, all right? But I'd like to do one other thing before the video is done. And so again, let's copy and comment that out and start anew. And in this case, I'd like to show you that this is not just for one particle. This can work for multiple particles. So in this case, I'll have x10, vx10, y10, vy10. And let's go ahead and do x2, vx2, y2, vy2. And so I'm going to have two particles. So why would I care about two particles? Well, I can have something like the Earth-Moon system where the Earth and the Moon are rotating about each other. All right. So I'm going to have x10, vx10, y10, vy10. Vy 1, 2, 3, 4, 5, 6, 7. Okay. So those are my initial conditions. Let's do the same time span. And let's just call this, I'm going to call it G2. So this is going to be the gravity between two particles. All right. And for good measure, let's call this M1. Well, let's just call this M. All right. So in this case, this all stays the same. So x1, vx1, y1, vy1. And I'm not doing it in the full dimensionality. Let's assume we're in the plane. That's why I'm not doing a z here, but you could easily add the z. There's no limit to the number of components you can use. 2 and 2, and of course I have to change this. 5, 6, 7, 8. So we have 8 components, right? The x and y position of both of them. And now let's, let's kill all this. And this is Vx1, Ax1, Vx, Ay1, and copy and paste. All right. So, right, all this was just our bookkeeping stuff to tell us how we're saving these guys inside here. All right. So we have 8 different things. That means we have x and y for two different particles, and we have vx and vy for those particles as well. So we have 8 inputs and 8 outputs, plus the time, plus the masses. All right. So what are the masses going to be? So now we need the acceleration. All right. So the force of gravity, right? So the force of gravity just equals m1 times m2 over r squared, right? So I need this, and I'm just going to call it r2. So I need a variable times r2, and notice I can just add anything I want in between here, any new functions, any variable names I want. R2 is just going to be x1 in minus x2 in quantity squared plus the same thing for y. Right? This is just the distance between the two particles. And if I just, maybe it's easier to just also make a variable called r, which equals the square root of r2. Whoops, wrong parentheses. All right, so we have that. So this is going to be the gravitational force between the two. I'll just call it Fg, force gravitational. But I don't want the force gravitational between the two. I want the components of the gravitational force between the two. All right. So in that case, I'm going to have, AX. So the acceleration in the x direction is going to be the force of gravity, right, times the difference in the position. So it might be helpful to actually call this dx. So we're going to have this guy called dx. So this is the distance between the two, and if we're going to have a dx, we just will have a dy. Make sure to change these guys. So we have the x's and the y's. And so imagine that if they're lined up along the x-axis, that means there is no force that direction, right? So this is a cosine of theta, and we can rewrite the cosine of theta as the opposite over the hypotenuse. So the acceleration in the x direction is going to be dx divided by r, right? This is just the definition of the sines and cosines. So this is going to be the acceleration. So force times dx divided by, oh, of course, divided by m1, right? So the force, and then the force, and then the angle of the force, and then divided by the mass. So this is the acceleration in the x direction. So this is ax1. All right. Let's just double check. So if x1 is at a big number, this is going to be a minus sign, right? So if x1 is at 10 and this is at 0, the force better be in the minus direction. So we'll need this. All right. Let's go ahead and say ax2 is going to be the same thing, but with a plus direction, and the mass is the mass 2. All right. And the video is getting long, but I promise we're almost there. 3 and 4, and of course this is just dy and dy. And I think that is y1 y2. All right. So that should be two bodies gravitationally attracted to each other. So again, this is just the law of gravitation. The force of gravity is just m1 times m2 over r squared. There's a big G out in front of that, the gravitational constant, but for now I'll just, well, I can put big G there if we want. Fine. So let's put big G out in front. This is the force, and then this gives me the sines and the cosines, so this gives me the angle of the force that acts as that, and then I got to change the force to acceleration by dividing by the mass. All right. So we don't need the linear drag, and now mass is itself actually a matrix, so we have m1, let's just say it equals 1, and m2 equals 1. Let's have m2 equal 100, so we'll have something heavy and something light. So m equals m1, m2. This is just a way, again, I'm storing multiple things in one variable in this way inside m. And again, we want to use the right function. Hopefully you can see this good. M1, N2, we need big G. Let's make big G equal to 1 just to start with. That makes it easy. M1, M2, initial conditions, time span, x1 out, vx1 out, y1 out, vy1 out. Again, just housekeeping. A parameters in, a parameters out. All right, so x1 out, y1 out. Comment out some of these things we don't need. And this might very well break, but let's see what happens. Integration was not successful. So I probably chose some poor numbers. I definitely chose some poor numbers. Let's try that. What is the heavy one? M1 is the light one. M2 is the heavy one. All right. Let me pause here a second. I don't want to confuse the issue of the programming with poor initial conditions. But you will find this sometimes. And this is basically, oh, well, I can see what the problem is. So basically what's happening is I have these two bodies, right? And I set them, I just let them go. And so they're crashing into each other, right? So it doesn't like this because basically I'm dividing by, this is dividing by 0 when they crash into each other. So I definitely don't want them to crash into each other. So I need to do something like that. So let me pause here for 1 second and do a little check to make sure I have good conditions, and then I'll be right back. All right, so that took a second for me to find the error, but the error was something very simple in this line. You notice I copied the x's and the y's to the x's and y, but of course this x should be x2 and vx2 and y2 and vy2. So the two particles, the two planets, were always exactly on top of each other. So of course this is not going to work, and this confused the program because that meant there was zero space between them, and that meant that gravitational pull was infinite. All right, so now that we have that problem fixed, we can run this. Good. And now we see the orbit of a planet over here on the right. But you notice it's not circular. Why is it not circular? Well, that's because I'm not looking at both the two planets, right? Realize that both the Earth is rotating around the moon, but if I look at the second part, the moon is actually also rotating around the Earth, right? So if we're looking at this, we can extend this a little bit longer. So you can see these kinds of trajectories where the two are being influenced by one another, right? And this will be even more the case if I start to make these similar masses. So now that they're similar masses, they're rotating more and more around each other. And if I make them even closer masses, right, 2 and 1, now we need a little bit more time to see what we're doing here. Let's do 6. Yeah, and now we can start to see them rotate around one another, and even longer. Now we can see this path, and let's make this 2. Good. And if we wanted this in time, we could even watch these two bodies as a function of time instead of as a function of position. Yeah, why not? Well, we're actually out of time for this video, so let's go ahead and stop there. But I think this gets you the basis of what you want to do, right? So we can see, we started out as a little review. We started out, we defined what a function of an octave is. We started out doing Euler's method, right? So we did the same thing we did in Excel with this time evolution. Then we moved to the ODE45, this is the 4th order Runge-Kutta, and got in the habit of giving the computer what it wants and doing this bookkeeping at the beginning and the end, and did it in 1 dimension. After we did it in 1 dimension, then we did something more complicated. We did drag in 1 dimension. And once we got a full handle on the drag in 1 dimension, then we moved on and did drag in multiple dimensions, right? So we did drag in X, Y, and Z. So we had 3 dimensions that we're calculating all at the same time. And then finally, the last thing we did was we moved on to 2 bodies, right? So we can do it in multiple dimensions for multiple particles. And there's really no limit to this, only the computational complexity, right? So if you want to do the Earth, the Moon, the Sun, the whole solar system, you can do the whole solar system. It's just going to be slow to compute it, and you'll have to get all the interactions right. And you'll notice the nice thing here is that basically it's some bookkeeping, but this bookkeeping is all the same. But the physics is all captured just in 1 or 2 lines, and you let the computer take care of all the time steps and everything else, right? So again, bookkeeping, the only real physics here is in this small part. All right, so that's going to be it for now. We might come back to this later in the series when we look at different examples. For example, electromagnetic particles, particles in electromagnetic fields, particles that interact with each other. But we'll use these numerical techniques as we're moving forward. All right, thank you very much, and we will see you next time.